Alrighty, welcome back to 454. So last time we were trying to chase cache optimizations and we didn't do very well. The example, we changed our memory usage and then we drove down our cache rate, but we didn't improve our performance that much. Kind of a confusing example. So today we are changing the example and just showing what you can do by just focusing on cache optimizations. So, big tip, this is for any performance programming course you want to write code that has locality. We went over it before, the two main types, temporal locality, aka you reuse memory over and over and over again. If you use it, you'll probably recently use it again. And then you also want to have spatial locality. You want to go to nearby addresses so that all the systems work nicely together. Computers like things that are always sequential. And how do we achieve locality? Well, we have to have a good algorithm. You might also have to focus on loop transformations or some other techniques that we will go into today. So, first off, bit of background that everyone should know how 2D arrays are laid out in C. It is row major, which means elements of a row are all beside each other in memory. So you can just think of it as a 1D array. I literally lifted this from APS 105, so I hope this is review. So if I have a 2D array, right, assuming I have an int array and a table and a whole bunch of elements like row, column, if I wanted to convert it to a 1D array, it would just be like my row index times the number of columns I have. So you jump columns at a time for each row, and then all of the columns are right beside each other, so I would just use the column index. That means table at row 0, column 0 is the first element in the 1D array. Row 0, column 1 is the next one, so on and so forth. So everyone's okay with this review? 2D arrays, how they're laid out in memory in C? If you use, what is it, Fortran or something like that. This is not true. It's column major, so it's the other way around. But probably most of you will not be unfortunate enough to use Fortran. Or maybe it's COBOL, one of those silly languages. Anyways, so for this lecture, most of the time we'll just be assuming a simple cache and kind of figuring out what our cache misses is. The example we will use today is a very, very simple cache where the block size or the line size or how big each cache element is 8 bytes. Therefore, right, if we were using an integer array, it could hold 2 ints in one specific cache line. And we'll assume we have a two-way associative cache with a single set. So this is actually the same as fully associative. So if I only have 2 blocks and it's 2 associative, means any block can go anywhere in my cache. This one, really, really small, only 2 blocks. So the total size is 2 blocks, and we'll assume least recently used as our replacement policy. So if we need to kick something out of cache, it is the block that was used least recently. So some questions you should ask yourself always when you are programming, especially using arrays, is how many elements are there for a block? Does my data structure fit in a cache? Do I reuse blocks over time? And what order am I accessing the blocks is, because all of these things will matter for your performance. So let's first start off with just analyzing a very, very simple array. So say we have, I don't know, we define n equals to 4. We create an integer array of 4 elements just on the stack, and then we have our for loop that just reads elements of A. So for our cache, we should be able to figure out what the miss rate is on this scenario. That is assuming the array is actually cache aligned. And then we should be able to figure out our miss rate, which is just the number of misses divided by the number of accesses. So first element that I access, is that a cache hit or a miss? Miss. And then what will, in this very, very simple cache scenario, what elements will it bring into cache? Yeah, A0 and A1, right? So it brings two elements into cache. Then the next element we look up is 1. It's in the cache, so that would be a hit. So now we're 1 and 1. Then next we index element 2. Is that in the cache? No. So we bring it in. It has another block, so it can be in the cache at the same time as the other entry, and the whole array fits in cache. So our last final access, we will have a hit. So in this case, we have what? 2 misses and 4 accesses, right? So here's it in the slide. Everyone okay with that? All right, should be fairly straightforward. So if you generalize that, right, in this scenario, if I can only fit 2 things in the cache, my generalized miss rate is like I'll have n divided by 2 hits, no matter what the size of the array is in this case, and then n accesses. So that gives me all the time I will have a 50% miss rate. So this is about the best we can do with a cache this small that can only hold 2 elements, right? So if we, I don't know, if our cache could hold 4 elements in a block, our miss rate would be what? 25%, assuming that the array is cache aligned, right? So if I was really unfortunate, if I didn't say, you know, assuming it's cache aligned, let's say this is my array block, I could have had it such that if I access A0, it's actually the last half of a cache block, and then my next one would be element 1 and element 2, and then my last cache block was 3. So this is what would happen if my array was not cache aligned, right? And in this case, I would have 3 misses. I would have 4 accesses. So I would immediately have a 75% miss rate if the whole array wasn't cache aligned. So I would start off really unfortunate. All right, so yeah.
Why would your cache not be, or sorry, why would your memory be not cache aligned?
So in this case, right, my array would be 4-byte aligned, but my cache is 8-byte aligned because that's my cache size, right? So the array could start at any 4-byte boundary. If it starts at the wrong one, I'm screwed.
Oh, so like your array in memory is not.
Yeah. So your array is at starts at byte 4 or something.
Yeah.
And caches want to start at 0 or 8.
Right. Okay. So you start.
Yeah.
If n is large enough, then eventually prefetching would kick in too, right?
Yeah, depending on, we'll talk about prefetching a bit in the next one, but yeah, prefetching will come in a bit and slightly help us out a bit. But yeah, any questions about that? All right, that is our 1D array. So let's add another loop. 1 loop is fun, 2 loops is more fun. So what is our miss rate now? So all we're doing is assuming we can just go over this entire array p times. So we can probably figure out our total miss rate. So inner loop, still the same, right? So inner loop, I'll get a 50% miss rate, but eventually, assuming that array is cache aligned again, then, well, it's a hit every single p times through the loop, right? Through the outer loop. So overall, in this scenario, since the whole array fits in cache, we only miss that n divided by 2 times the first time we access the array. Then the whole array fits in cache. So every time we iterate through this outer loop, then, well, our whole array is in cache, so they're all hits. So the more times we run the outer loop, the more hits we get, and the better our hit ratio. So the number of accesses we have is just n times p, so our overall miss rate is now 1 divided by 2 times p. So this assumes the whole thing fits in cache. Now, if we had this scenario where our little array was not cache aligned, what would our entire miss rate be? Yeah.
Would it be the same as before? Because every single time you would have to reload each, you would have to keep swapping them.
Yeah, same as before, it'd be 50%, right? Is that what you're gonna say?
If it's not cache aligned,
Yeah.
then there would technically be 3 blocks of cache that we need to put in, right? But we only have 2 ways. So wouldn't it get evicted every time?
Yeah, it'd get evicted every time, so it's like running it without it being in cache every time, so our miss rate would be 50. Or no, it'd be 75, sorry. Yeah.
Yes.
Yeah, 75, sorry. So every time through, right? First time through the array, if it was not cache aligned, we'd have A0 in, and then, okay, well, that was a miss, nothing we could do about it. A1, when we access that, it would bring in A2. So miss on 1, whoops. I assume it was that, yeah. So miss on, we have a hit on A0, miss on A0, brings in only A0. Hit on A1 brings on A2, so that would be a miss on 2. And then since we're assuming we only have 2 blocks that fit in cache, we'd have to evict the least recently used, which is this one. So it would get replaced by this. And then next iteration of the outer loop, we start again, and it's the whole thing again, where we would bring in the unaligned A0, and then our total miss rate would be 75% if the whole thing does not fit into cache. So cache alignment, even for that little example, really, really important. So, So everyone okay with that? Still simple things? All right. Wow, this lecture will also go quite fast, probably. So if the data does not fit in cache, so assuming our cache size was not big enough, then our miss rate would go back to that 50% again. So say we only can hold 1 cache block at a time. Every time through the loop, we would miss, load in another element, hit on the next one, so on and so forth. So being able to fit in cache is very, very important for our miss rate, especially if we have multiple loops going on at the same time. So, oops. Yeah, what about if we just had a 2D array instead of an outer loop going over and over and over again? So let's just assume that now we have n equals to 2, and we have a 2x2 int array now. So assuming that whole array is cache aligned, what is our miss rate now? Yeah.
50%.
Yeah, 50% again, right? It's the exact same thing as before. We're accessing it in row column, so we're accessing it the same order we would do in a 1D array. It's only 4 elements, so it's the exact same thing as before. So miss rate, exactly the same thing in this case. Being 2D did not affect anything, right? Doesn't matter if the entire array fits in cache or not in this case, because I'm accessing just every element once in this case, so it doesn't matter. Yeah?
Isn't the declaration of A wrong here?
Yes, the declaration of A is definitely wrong. Oops. So, not our example, so yeah, I'll fix that in the slides, but it should have 2 ends. All right, so if we just changed the boundary, or if we just change the accessing it, and this goes to the loop interchange again, like we saw before, again, this definition's wrong. But assuming we just flipped it around so that we access the columns and then the rows, so we just jump by columns at a time instead of rows. Well, what is the miss rate now? Well, in this case, I screwed up the indexes. So in this case, I just converted it to the 1D equivalents. So if you miss on 0, 0, instead of just 0, it corresponds to array if it was a 1D at 1. So that would bring in A0, A1 into cache, and then the next access would actually bring in A2, right, which is another miss. And then that would bring in A3. And then after that, since you're doing it in this order, you would access row 1, column 0, which would correspond to A1, which is now in cache, and the other one would also be in cache. So the miss rate is 50% if this whole array fits in cache, same as sequential. So the thing to mention here is even if you access it the wrong way, so if I access it in column major order instead of row major order, as long as the whole thing fits in cache, it doesn't matter, right? I can kind of skate away with it and not really notice anything. So that is the main point here. But things get real bad once that is not true and it doesn't fit in cache, right? So if it doesn't fit in cache and I access it in the wrong order, so say now I have a 4x4, now what's the miss rate now? So if we convert it to a 1D array, our accesses are going to be to A0, then A4, then A8, then A12, then A1. So if we do this now, right, what's our miss rate now? If those are our array accesses and we can only fit 2 blocks in cache, yeah. Other way.
Oh, whoops, 0. Wait.
100.
I said, oh, I said
I thought I heard 0. Okay, sorry. 100% miss rate in this case, right? So I access A0, that would bring into cache A0 and A1. Then I access A4, that's a miss. I would bring in A4 and A5 into cache. Again, assuming the whole thing is cache aligned. Then I access A8, I have to kick out that A0 and A1 and put in A8 and A9, etc., etc., etc. So our miss rate now, 100%. Whoops. So definitely something you want to avoid. That is why loop interchange is such a good thing. But sometimes, you know, the compiler can't catch it or it gets a bit more complicated. So that is why you should double check that your compiler actually did it correctly and you're actually accessing things in row major order. Most of the time your compiler should do it for you, but again, this is so important even for that tiny cache. Changes our miss rate from 100%, which is you know, terrible, to 50%, which is much, much better. All right, what about if we have something more complicated like matrix multiplication? Ooh. So if we have matrix multiplication, easiest way to argue about this is what happens when I equals 1 or I equals 0 whenever we're calculating a single element. So for this, let's just say I is constant at 0, so I'm accessing things in the same row for matrix A. But because the way matrix multiplication works, I can't do the same thing for matrix B, right? Because I have to access, you know, I mean, the way matrix multiplication works, it's row times column, right? Each element, you multiply them together and then add them together. So what is going to be our miss rate for just a single iteration of that outer loop? It should actually say when I is equal to 0. So when I is equal to 0, what elements am I going to access in which order? Yeah. 75%. Yeah. So it is 75%, and let's go over that real quick. So if I'm doing, matrix multiplication, right, and I assume that I is equal to, let's just say 1, what I'm doing in each iteration of, let's say, 4j, 4k, and then I'm doing, in this case, let's just assume that I is constant. I do something like this, times b J. All right, so if I do something like this, the first time through, I will access A0 and then B0, 1. So first time through, that's what I'll be accessing. And then, oh, wait, no, I made a big diagram. Sweet. So, whew. Why am I drawing stuff? All right, I already spent time to do this. All right, so the miss rate when I equals 1, well, typo, it should be I equals 0. So first time through the loop, I have the cache at the bottom. Right now it's empty. So assuming the first time through this, first element I'm going to access is A at 0, 0. So that would be a miss. So it would bring A00 and A01 into cache, the two things that are actually beside each other in memory. And then it would actually access this, right? It would access B00. So B00 brings that into cache. So it would bring B00 and B01 into cache. And now the next two elements it's going to access are A10 and B10. A01 and B10. Ugh. So is A01 in cache? Yes, so that would be a hit. So put it in blue. And then we access B10. Is that in cache? No, so what gets kicked out? Well, this would get kicked out, right? It was least recently used. I did not use it. I used the A1 instead. So this would get kicked out and replaced by B10 and B20. Not the greatest. Next element I access is A02. Is that in cache? No, I would have a miss, and I would bring in A02 and A03. Then I access B20. Well, that's not in cache either. That is another miss. So I would bring in B20 and B21. Then now I access A03. Well, now it's in cache, so that would be another cache hit. And now the next element I'm going to access is B30, which is not in cache, so it would be a miss and it would be brought into cache. So our miss rate in this scenario was what? 75%, right? So should be able to analyze the miss rate for this. So fairly straightforward so far. Okay, so if we were to generalize this, assuming that a row does not fit in cache, the arrays are cache aligned, and we can fit D elements in our cache, well then our overall miss rate will be 1 out of D, so every one element out of the cache line I'm going to miss times however many elements are in a row, so I'll be able to take advantage of my cache for a row, and then for every column I'm going to have n misses every single time it's going to be a miss out of my n accesses across the A array and my n accesses down the B array. So therefore, the total miss rate is, if you play with the numbers, is 1 divided by 2D plus 1/2. So I can never get better than a miss rate of 50%, no matter how big my cache is, right? So I'm kind of capped by that, which kind of makes sense. This half comes from every single miss happening when I access the array by columns. So to improve cache reuse, right? Misses are very expensive. L1 cache references, right? It's like just 1 nanosecond or maybe 4. Cache sizes are 32 KB, pretty small, pretty big, or pretty small, but big enough. And main memory references, right? They're like 100 nanoseconds and you have gigabytes. So matrix multiplication, if you actually look at it, it has a lot of data reuse, right? I use the same row multiple times in a row, same column multiple times in a row. So the key idea, if we really want to speed up matrix multiplication, is to try to cache an entire block once we load it. So we need to work with both rows and columns. Kind of easy to, cache the row. We can have our miss rate very, very low. But for the columns, we might have to do a little bit of magic. So some solution which might apply to some of your labs is you can operate in little subsquares of matrices. So the idea here is just to have one subsquare per matrix that fit in cache simultaneously. And then you're actually heavily reusing all the subsquares before loading new ones. And this is called tiling or blocking, however you want to refer to it. Oops. So I'll draw out the idea first. So the idea before was, hey, right, if I want to calculate this element of my matrix, well, I have to access this from matrix, let's give them names. So I have to access this element. Actually, I'll change the colors. So to calculate this one, which would not be in cache in matrix C, right, I would need this element in matrix A. And then if I access that element in matrix A, it would bring in the entire cache line, right? And then if I access this element in B, it would bring in this cache line. And then next iteration, well, this one would be a hit, but this one in, whoops, uh-oh. But this one in matrix B, like before, would be a miss, and we'd have a miss every single time we access the column. So essentially, we would have something that looks like this. And then this one would be, miss, then hit, miss, then hits, so on and so forth, right? So if we can't fit in a cache line, this is just really bad. We want to try and reuse that column as much as possible because we would have brought in all this data every time we brought in a cache line, right? We didn't actually use it. So to use it, that's where the tiling idea comes in. So since I brought this in and I assume that I can't fit an entire column's worth of blocks into cache at a single time, like by the time I wrap around and come for the next iteration, I assume that my cache isn't big enough to still have those entries in it. If I want to make sure that it has those entries in it, that's where the tiling comes in. So instead of doing this, accessing every column and having it wasted by the time I get back and having it kicked out of cache, the idea of blocking is I instead let it get to maybe here, whatever I can fit in the cache line, and I just stop there. And then for my rows, I can just actually do the same thing and just stop with a certain block of rows and calculate that subsection of matrix C. So this little block of matrix C, I can just divide it into blocks. So I assume that I can fit all these blocks from all the matrices into cache. And then I just calculate all the elements that use all of these rows. Let's assume that we just have one and then a hit. And then we just have one and then a hit for all the rest of them. So I will calculate all of the elements of this matrix from the row and column of all of these two little boxes inside the other matrices. And that way, my miss rate for this one will be, well, depending on my block size, I'll have one miss out of however many elements I can fit in a cache line. So over my d-axes, I'll only have one miss for both of them, right? And I reuse them over and over and over again. So does that kind of make sense? Yeah.
Why does the row for our subsquare in A, why is that not able to fit in the cache? Like, why is it yellow? I assume yellow's in this, right?
No, looks yellow. Green's a hit. Yeah, it's supposed to be green. It's green on this. I guess the color calibration. Yellow, whatever it's supposed to be. So they're all hits. Yeah.
In A, wouldn't the red dots be going across the top row? Or wait, sorry, wait, am I?
Yeah, they should all be like the sequential ones, right?
Yeah.
All the other ones. So we're not going all the way in the row. We're just calculating that box. And then to calculate the rest of this box, right, we would go ahead and move this square. So we'd move this square over here and then this square down. And then we'd have the same cache behavior. They all fill up, assuming that we can fit these 3 blocks in cache all at once. And then to complete it, right, we can go here, do the next subsquare, then do the next subsquare, and do something like that. So we would So for this, basically we would have squares going this way, then squares going this way, and everything fits in cache all at once. So we just divide it into smaller chunks that actually fit into cache. So that okay-ish? Yeah.
What if our application was, instead of reading from B, if we were just writing to B,
Yeah.
tiling still have a positive effect?
Yeah, so if we were just writing to B, depends how we're writing. In this case,
If you're writing in column order, specifically.
yeah, if you're writing in column order, since you have write back, it would probably speed it up a bit, so it would help writing as well as reading.
Okay, so you're saying by tiling, you're minimizing the amount of write backs?
Yeah, so I'm updating that like whole cache line before it gets written back, which is going to be a lot faster than only updating one element, it gets written back, and then I have to do it like 8 times, or 12 times, or 14, 16 times. There, powers of 2. All right, so let's go into fun demo. So here's normal matrix multiplication, right? Nothing too bad about that. So just gets the constant. This matrix n is just something I can set. And then I just, from I to j to k, ij equals ik, kj, blah, blah, blah. That everyone agree with that as matrix multiplication? All right, so let's try it out. So if I do something like, it's not that interesting by itself. So let's just run it. We're going to compare it to tiling. So tiling, the tiling version looks like this. So first off, if my cache size is 64 bytes, and these are arrays of ints, what should my tile size be? How many elements can I actually fit into cache at once? 16, exactly. So 64 divided 4, I can fit 16 in at once. So if I was to convert this and tile it, this code looks fantastic. So instead here, I tile every 16 because that is my cache size. And then I change all of my outer loops to, instead of going up by 1, it goes up by a tile at a time, right? So that's why it's plus equals t. And then now I just have a for loop, and these 3 for loops are for a single tile. So I need an I1, so that goes for everything in the tile. Then J1, everything in the tile. K1 everything in the tile, and then I just keep on adding elements to the resulting matrix by just building it up based off this tile. So, any disagreements with that beautiful code? It looks like it's supposed to be a lot slower, right? It just looks like, I mean, it's 6 loops versus 3. Wow, that seems horrible. But if I run it, let's see. So if I run it and both of my matrices are 16 by 16, should I see any difference between using this and using the boring old matrix multiply that I don't do anything for? Probably not, right? So if I do this, I run it, I get essentially the exact same thing. My miss rate is essentially 0. So the parameters I use here, this is the dimension of the matrix. So it's in this case, 16 by 16. And this is how many times to repeat it. So if I repeat it 1,000 times and the whole arrays fit into cache, yeah, I expect my L1 miss rate to be pretty much 0, especially if I do it a bunch of times. If I do it only one time, right, I'll have a larger miss rate, which gets closer to that 1 over 16. There's some things going on with prefetching and things, but that's why it gets to something like this. And the difference here is essentially just noise. It doesn't really matter at this point because it's doing so little work. All right, so if I bump it up to 32, likely my cache is big enough that this is still mostly okay. Oh, no, even with that, even with 32, bumping it up to like a tile 4 by 4, since the cache is so small, I still get some sort of benefit, even though my miss rate is abysmal. Actually, those should be the same. Maybe it just got noise again. All right, tiling's even better for 32 by 32, learning things on the fly. So, even though my miss rate is essentially 0 for both of them. But as soon as I grow my array a little bit, the effect becomes more and more pronounced. So say if I had a 64 by 64, again, here it still kind of fits in cache, so maybe not. If I bump it up to a 128 by 128, then suddenly my effect becomes way bigger, right? So now I've created an array big enough that if I just do the naive approach of just having this type of loop, every time I access any element in the B array, it's a miss every single time, right? Even though my L1 miss rate is 100, which tells me that, hey, my array kind of fits into L2 cache. So this is primarily just the effect from the L1 cache. So just by accessing, tiles and actually reusing the columns I bring into memory, I get my miss rate from 82% all the way down to less than, well, not less than 1%, but around 1%, right? Cool. So, should get more pronounced the bigger and bigger I make my array. Whoops. Should still work. So, if I make it 256, I lose some effect here, but still like 2 times better. And again, if I bump it up, let's say to 512, now I have to wait a very long time because now likely my row doesn't even fit into cache. By the time I reuse that row again, since it's not in cache, I have to refetch the entire row. I don't get the advantage of having hits all across a row. And yeah, that is a 10x increase there. So very, very, very important if you can just constrain your caches to actually just make sure that you fit in cache. Make sure you reuse your data, even if you have to do something as nuts as writing 6 for loops, right? The 6 for loops, even though it looks maybe at first glance that the person writing it is actually insane, it's actually a lot faster because it accesses memory in a way that is much, much more cache friendly. So, any questions about that? Cool, right? Tiling, very, 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 very good, yeah.
Are there any compiler analyses that can do this automatically for you?
Are there any compiler analyses that will do this automatically? Not that I know of. Especially once it gets into, like, this is really hard for a compiler to, like, even matrix multiplication, kind of hard for a compiler to argue about, like three different arrays all using different indexes. So yeah, compilers not that great at this. And GCC, I had to use Clang for these examples because GCC completely screwed this one up too. It did not vectorize and I couldn't actually compare things. So another plug for Clang being much, much, much better. All right, any questions about this fun stuff? I mean, that was pretty much the lesson of the day. So the misanalysis for the tiled one, in general, if we can assume we fit each tile into cache, so that means your cache size in this case has to be bigger than 3 times t squared, sorry, not t to the 3. So your miss rate for the tiled A matrix and the tiled B matrix would just be 1 or 2 divided by t misses out of the 2n accesses. So for each array, right, you would have, depending on your block size, the first one would be a miss, and then the other, in this case 15, were all hits. So we made our tile size match, and then we would have that for both the B array and the A array, and in total we would have 2n accesses, giving us a miss rate of just sequentially accessing an array, even though in one we're going in column order now. But because we're tiling, we get our nice sequential miss rate of 1 over t, which is a massive difference from before. So we even did a little bit better because what? 1 divided by 16 is what? Like 1 divided by 16? It's like a 6% miss rate, but we saw when we actually ran it, we got like a 1%. Has to do with a little bit of prefetching, a little bit of the tiles in the corners can kind of overlap once it gets kind of to the side. So we can actually take advantage of some things. But massive, massive difference from before, right? Tiling is big good. I'm out of slides. So we're slightly, if you can believe it, we're slightly ahead of the other class. I'm not sure. Yeah, I ran out of slides. So yeah.
With the right allocate cache policy, would loads and stores kind of behave the same? Like if you're storing to an address, that would first have to bring that line to cache, and then you modify that cache line, right?
Yeah. So sorry. What's your question?
Like I guess under normal circumstances, do loads and stores affect cache differently?
The loads and stores, the way most things are set up, generally not really. You'll have more of an effect if you can cache a bunch of writes all together. But it also kind of depends on your program whether or not, and your hardware, whether or not it can kind of hide that, just based off, you know, how much you actually use memory in your program. So it kind of depends. Hardware is complicated. That's the great thing about this course is we can just say it depends for literally everything. All right. Any other questions? Holy hell, that went way faster than I... Yeah, I literally have no... Yeah.
How does the material that we're learning in class, how would that be tested on a midterm or an exam?
How would that be tested on a midterm or exam? I have to look at the previous midterms. I assume it would be like something like, hey, you should be able to argue about how a piece of code would, you know, interact with a cache of a certain size and blah, 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 I assume. Yeah.
Just to make sure I understand about the what you explained for tiling.
Yeah.
Assuming that we treat our tiling block sizes correctly,
Yeah.
the miss rate for just the B block becomes the same as the miss block for the A block, right?
Yep. Yeah, so we're doing it in a way that if we bring in a whole cache line, if we're tiling, we actually use that whole cache line, right? So we take, yeah.
So we should like calculate our C values by going, I guess, column major to get everything in cache for C.
Yeah, so basically everything I bring into cache, or you're saying for matrix C?
Yeah, for matrix C, like for the tile,
Yeah.
we should be going column major, right?
For matrix C, it doesn't matter if we're doing, like if we're doing this tiling approach. If we're doing this tiling approach, it doesn't matter. If we're doing the other one, depends how big the cache is, but we calculate the rows of, we access the C matrix in row major order. So that didn't really help us. Tiling is just making sure it all stays in cache and doesn't really matter that much for matrix C. That's why we mostly argued about, well, matrix B was the bad one. All right. I will stick around for about an hour. We